Hello everyone! I am Anna and I'm going to present you the tree-added distance described in a paper of Zhang and Shasha called Simple Fast Algorithms for the Editing Distance Between Trees and Related Problems. You can find the link in the description. So first of all, I will explain you how the general edit distance is defined and give you a short insight into the string edit distance, also called Levenshtein distance, because it is very similar to the tree edit distance. If you already know how it works, you can skip it and continue with the tree edit distance. The edit distance is defined as the shortest sequence of edit operations which transforms x into y. As edit operation, you can use a deletion, insertion, or a replacement. If we talk about the Levenshtein distance, which is a string edit distance, these operations are executed on characters. Later we will see that the tree edit distance is a generalization of the string edit distance. So now let's take a look at an example. We want to transform the word moon into the word lions. Which operations do we have to perform? First of all, we replace the M with an L, so from moon we get the word loon. Then we replace the second character O with an I. The next two characters, O and N, we don't need to change. And finally, we have to insert an S and we get the word lions. If we assume that each operation costs 1, then the minimum edit distance between moon and lions would be 3, because we performed 3 operations. We have just done this based on our intuition, but how are we going to compute the minimum edit distance? The standard algorithm is with dynamic programming, which is a tabular method of computation. This is the dynamic programming table. It is all about the subproblems. So, what does each of these cells represent? Each of these cells are a subproblem. Let me show you an example. Do you see where the yellow cell is? What does the yellow cell mean? It is a subproblem. Each of these cells are a subproblem. The original question we asked ourselves is the red cell. What is the edit distance between the two full strings? Going back to the yellow cell, what does it mean? It tells us what is the distance between MO and L. MO is the substring we take from moon and L is the substring we take from lions. Each of these cells represent a subproblem, building up to the final answer in the red cell. Let us define the minimum edit distance formally as capital D of ij, where I corresponds to the index of the substring's last letter. In this case, the index is the first O from moon. And j corresponds to the index of the substring's last letter from the other word, in this case 1. So the yellow cell defines the minimum edit distance d of 2 and 1, meaning between MO and L. And the red cell defines the minimum edit distance d of 4 and 5. So now let's walk through the table and initialize it with the first values. First of all, this letter right here is called lambda, which stands for an empty string. If I need to transform an empty string to an L, I need to do an insertion. So from empty string to L it costs 1 because we insert the L. From empty string to Li it costs 2 because we do 2 insertions, and so on. Let's go the other way around. If I have the character M and I want to transform it to an empty string, that is 1 deletion. So we have to add to the 0 of the empty string plus 1. If I have MO and I want to transform it to an empty string, that is 2 deletions, and so on. So now let's continue with the other cells. The next cell would be the yellow one, which is by our definition capital D of 1 and 1. Does M equal L? No, we have to perform an operation. The minimum edit distance is defined as the minimum of 3 operations. The deletion plus 1, which would result in 2, the insertion plus 1, which would also result in 2, and the replacement plus the distance between the two characters. If they are the same, the distance would be 0. In our case they aren't the same, so the distance is 1. And 0 plus 1 is still 1. So, which is the minimum of these 3? 1. We choose to do a replacement. We replace the M with an L. The next cell would be this one. In this case, the lowest cost is 2, which could be calculated from 2 different operations: insertion and replacement. The reason for this is that you either replace the M with the L and then add the I, or the other way around. You add the L first and then replace the M with the I. Both cost the same, so you can choose which way you want to go. If we continue calculating the subproblems, we come to the cell here. This one is special because we compare the O from moon with the O from lions. The distance between these two letters is 0, which is why the third operation will be the one with the lowest costs. We simply could use the value d of I minus 1, j minus 1, so the result would be 2. If we continue filling the table, the minimum added distance of the two strings appears in the lower right corner, which we already knew is 3. Now we can clearly see which paths or which operations we have to choose for the global optimal solution. First we replace the m with an l, then we replace the o with an I, the o and n could remain, and finally we insert an s, which results in an added distance of 3. Let's continue with the tree added distance. First of all, the operations are the same as on strings, only that they are executed on nodes. So we've got the deletion, insertion and replacement of a node. Let's take a look at an example. We want to compare tree 1 with tree 2. The distance between them is the number of added operations we need to transform tree 1 into tree 2. The gray nodes of tree 1 can remain because they appear in the same order in tree 2. The blue node of tree 1 has to be deleted, and the green node has to be inserted. The blue node can simply be moved to another position, because the order of the parent and child nodes would be mixed up. This is called the mapping. If we assume that each operation costs 1, then we could see directly that the tree added distance is 2, because we need 1 deletion and 1 insertion. We have just done this based on our intuition. But how are we going to compute the minimum added distance? Just like the string added distance, the standard algorithm is done with dynamic programming. First of all, we number the nodes of the two trees. We still need the labels of the nodes, but for now let's look at the indices. We got 6 nodes in tree 1 as well as in tree 2. So we create a dynamic programming table with the number of nodes in tree 1 on the left side and the number of nodes in tree 2 on the upper side. So what does each of these cells represent? The red cell is the solution of our original question. What is the tree added distance between the two full trees? We define this as tree distance between nodes 1 to 6 of tree 1 and nodes 1 to 6 of tree 2. We could also write it as tree dist 6, 6, which means the same. But back to our subproblems. What does, for example, the yellow cell mean? It is the distance between nodes 1 to 5 of tree 1 and 1 to 5 of tree 2. Now we see that the parts of the original trees are no longer connected, which means that we have several subtrees from tree 1 which we want to compare with subtrees from tree 2. Multiple trees make a forest. Therefore, we do not use the tree distance but the forest distance. So the value of the yellow cell is the forest distance between nodes 1 to 5 of tree 1 and the nodes 1 to 5 of tree 2. We could also write it a little bit shorter, forest distance 1 to 5, 1 to 5, because the first nodes always refer to tree 1 and the others to tree 2. Did you notice that node 1 is the leftmost leaf of the root node? Let's call the root node of tree 1 I1 and the root node of tree 2 J1. Both I1 and J1 are node 6. In both cases, the leftmost leaf of the root is node 1. So we can define the forest distance as the distance from the leftmost leaf of I1 to I and the leftmost leaf of J1 to J. Okay, now, how could we compute the value of the yellow cell? Do you remember the 3 operations? The first one is the deletion. So we would take the result of the gray cell, which corresponds to the gray nodes, and delete one node, the blue one. By performing the deletion, we have to add 1 to our previous result. The second operation would be the insertion. We would take the result of the gray cell and insert 1 node. By performing the insertion, we again have to add 1 to our previous result. The third operation that we could choose is the replacement. But in the case of forest comparison, the third operation is a little bit different. We take the result of the forest distance 1 to 4 and 1 to 4 and add the result of tree distance between the other nodes. Here on the left side is a summary of the operations that we can perform in a forest comparison. Have you noticed that the third arrow is missing in operations? This is because the third operation does not necessarily start from the field in the upper left corner. Here's a small example. We look at the yellow cell. What does the yellow cell mean? It is a subproblem. The comparison between nodes 1 to 3 of tree 1 and nodes 1 to 6 of tree 2. Again, we have to compare forests, so we use the forest distance. We split the two calculations. The first one is the forest distance between the node 1 and nothing, and the second would be the tree distance between the trees rooted at nodes 3 and 6. We get the result of the first calculation out of the gray cell, and then we have to add the tree distance. So let's take a look at another example. What does this cell mean? It is the distance between nodes 1 to 4 of tree 1 and nodes 1 to 3 of tree 2. This time we have two trees that we compare with each other. So the value is calculated differently than with forests. However, we can still call it forest distance because a forest can also consist of a single tree. Only the calculation is a little bit different. The first operation remains the same. We take the result of the gray cell, represented by the gray nodes, and delete the blue one. Because of the deletion, we have to add 1 to our previous result. The second operation would be the insertion, which also remains the same. And the third one would be the replacement. This one is different for trees than for forests. Here we compute exact the same thing as for the string added distance. We take the result of the gray cell and compare the nodes 4 and 3. The labels of these nodes are D and D. Do they match? Yes, they do. So the distance between them is 0, and we could just use the result from the gray cell. Okay, so back to our operations we do when we compare forests. Sometimes we need to add a tree distance to our computation. So what we have to do is to calculate all tree distances that could be needed at this point, before we even start calculating this table. Which subtree distances do we have to calculate? To answer this question, we will mark all nodes in the same color which have the same leftmost leaf. Let's take a look at tree 1. Nodes 1, 4 and 6 have the same leftmost leaf, which is node 1. Nodes 2 and 3 also have the same leftmost leaf, namely node 2. And node 5 is its own leftmost leaf. From this point we can calculate the key roots. The key roots are the highest nodes which have the same leftmost leaf. So if we take the highest nodes of each color, we get the so-called key roots. The key roots of tree 1 would be 3, 5 and 6, and the key roots of tree 2 would be 2, 5 and 6. For each possible combination of these nodes we now have to calculate the tree distance. We save the tree distances in a table so we can recall them later. The first combination would be the tree rooted at node 3 compared to the tree rooted at node 2. First of all, we number the nodes and create the dynamic programming table. Then we initialize the table by the distance between an empty tree and the node 1 of tree 2. For this we need to do an insertion, which costs 1. Next we calculate the distance between node 1 of tree 1 and an empty tree. And finally we compute the distance between node 1 and 2 and an empty tree. For this we do two deletions. The next one is the distance between node 1 of tree 1 and node 1 of tree 2. Since both nodes have the same label, the distance is 0. The distance between these two trees can now be entered in our tree distances table. Here we must be careful to use the indices of the entire tree. And so we continue to fill the tree distances table. The next combination would be 3 and 5. And this one is 3 and 6. In this case, some of our computed values are forest distances. They are marked in gray and should not be copied to our tree distances table. For example, the distance between node 1 and node 1 to 2 is a forest distance. So let's continue with the other combinations until we filled all values of the tree distances table. So finally we reached our desired comparison. And the result of the comparison is as always in the bottom right corner. Now we can clearly see which paths or which operations we have to choose for the global optimal solution. The A must not be changed. Neither does the B. The C has to be removed. The D matches the D. The C has to be inserted. And the E and the F don't need to be changed. The algorithm in pseudocode looks like this. First we compute the key roots of each tree. Then we compute for each combination the tree distance. The computation of the tree distance looks like this. First we initialize the left column by performing deletions. Then we initialize the upper row by performing insertions. And then we compute for each cell the forest distance. If the comparison is between two trees, we can save it in our tree distances table. And otherwise, we can use the tree distances table to calculate the forest distance. That's it. Thanks for watching.